Welcome to another deep dive. Today we're going to be looking at the making of the atomic bomb.
Oh, that's a great one.
It's a big one.
Yeah, it's a big one.
A long one, a lot to cover, and we're going to explore this incredible period, of scientific discovery
Yeah,
that had such world-altering consequences.
for sure.
And we'll be doing what we always do, pulling out those thought-provoking details
Yeah.
that, make you kind of rethink things.
Yeah, make you rethink what you thought you knew.
What you thought you knew about the dawn of the atomic age. So,
Yeah, one of the things that the making of the atomic bomb really highlights is the collaborative nature of scientific progress.
yeah.
It's like what Michael Polanyi describes as this, giant brain of interconnected minds.
Right.
Each discovery builds upon the work of others.
It makes you wonder, how much do we rely on that giant brain in our own lives? Think about how you stay up to date in your own field.
Yeah.
Are there journals you read religiously, conferences you attend?
Yeah.
Maybe a trusted network of colleagues you bounce ideas off of.
Yeah, for sure.
It's all about being plugged into that shared knowledge, isn't it?
It is. But as Richard Rose points out,
Yeah.
in the book, this collaboration
Right.
also has inherent limitations.
Yes.
The physicist Eugene Wigner noted that physics often focuses on finding correlations,
Yeah.
not necessarily complete information.
Right.
So what happens to the information that falls outside those correlations? What are the blind spots in this giant brain?
Right. What's left out?
Yeah, what's left out? Exactly. And
Yeah.
speaking of missing pieces,
Yeah.
the book mentions some fascinating near misses in scientific discovery.
Oh, yeah.
Like the story about Frederick Smith almost discovering X-rays.
Right? It's incredible. He dismissed these fogged photographic plates near his cathode ray tube as just an annoyance.
Wow.
Can you imagine if he had dug a little deeper?
Oh, he would have been.
He might have stumbled onto X-rays years before Roentgen. Yeah.
That's a reminder of how crucial it is to pay attention to unexpected results.
Right.
Sometimes the most groundbreaking discoveries are hiding in plain sight.
It really makes you wonder how many other scientific breakthroughs we've missed simply because we weren't looking for them.
Right.
But luckily, J.J. Thomson was a bit more attentive.
Yeah.
His work on cathode rays led to identifying electrons,
Right.
which was a huge step in understanding the structure of the atom.
Huge. Yeah,
But it was Ernest Rutherford who really shook things up.
for sure.
He was initially focused on radioactivity.
Yeah, especially his discovery of alpha particles.
Right. And then in 1911, he conducts this famous gold foil experiment,
Yeah,
and boom, the atomic nucleus is revealed.
just like that.
It's amazing how such a seemingly simple experiment could completely revolutionize our understanding of matter.
It really is. It's a perfect example of how a single experiment can shift an entire scientific paradigm.
Wow.
Even James Chadwick, who later discovered the neutron, described attending Rutherford's lecture on the discovery as
Yeah, a shattering experience.
yeah.
It was a true aha moment.
Yeah.
But Rutherford wasn't just a brilliant experimentalist. He was also instrumental in recognizing and nurturing other brilliant minds,
Right.
like Niels Bohr.
And Bohr was initially this intriguing figure.
Yes.
To Rutherford, he was a football player who defied Rutherford's expectations of what a theoretical physicist should be.
Yeah. He had that image in his mind of what a theoretical physicist should be, and then this football player shows up.
And yet Bohr turned out to be a game changer
Oh, for sure.
in the world of atomic physics.
Absolutely. And what's fascinating about Bohr is how he built upon Rutherford's discoveries.
Okay.
He took that model of the atom with its nucleus
Yeah.
and proposed that electrons orbit the nucleus in specific energy levels.
Okay.
And then he derived Rydberg's constant, a mathematical formula that had been observed in spectral lines, but no one understood why it worked.
Interesting.
Bohr's model not only explained it, but predicted the spectral lines of hydrogen with incredible accuracy.
It was a huge leap forward.
So it's not just about having a good model.
Yeah.
It's about having a model that makes testable predictions
Yes.
that can be verified.
Right.
That's what makes science so powerful. It's not just a collection of ideas. It's a way of understanding the world through observation, experimentation, and rigorous testing.
And that brings us to perhaps one of the most revolutionary periods in physics.
Yeah.
The rise of quantum mechanics.
Okay.
This is where Werner Heisenberg enters the picture.
Okay.
A young physicist who developed a whole new way of thinking about the atom,
Okay.
relying on abstract mathematics and what he called a strange algebra.
That's where things start to get really mind-bending, right?
Yeah.
We move away from this neat picture of electrons orbiting the nucleus like planets around a sun.
Right.
And we enter a world of probabilities and uncertainties.
Exactly. And it challenges our very notion of what it means to observe and understand reality.
Right.
As Einstein famously said, it is the theory which decides what we can observe. That statement has profound implications for how we approach scientific inquiry.
Yeah, it's like our tools for understanding the world actually shape what we are able to see.
Yeah.
But let's break down this concept of uncertainty a bit further. What exactly is Heisenberg's uncertainty principle?
It basically states that we can't know both the position and velocity of a particle with perfect accuracy at the same time.
Okay.
The more precisely we know one, the less we know about the other.
Okay.
This wasn't just a limitation of our measurement tools, it was a fundamental principle of nature.
So it's not that we just haven't figured out how to measure both accurately. It's that the very act of observing one affects the other.
Exactly.
That must have been a pretty unsettling concept for physicists at the time.
It certainly challenged the classical view of a deterministic universe.
Yeah.
Imagine the universe at its most fundamental level isn't a giant clockwork mechanism ticking away predictably, but a realm where chance and probability play a central role. Even Bohr and Heisenberg debated the interpretation of this principle.
So even the people who came up with this groundbreaking idea
Right.
couldn't fully agree on what it meant.
Exactly. And all of this is happening while the world outside the lab is becoming increasingly unstable.
Right.
It's the 1930s, Germany's in turmoil, and the rise of anti-Semitism is forcing many brilliant scientists, including Einstein, to flee.
It's against this backdrop of political and scientific upheaval
Yeah,
that the discovery of nuclear fission occurs.
right.
In 1938, Otto Hahn and Fritz Strassmann, working in Berlin, stumble upon something truly unexpected.
Yeah, they were bombarding uranium with neutrons, expecting to create heavier elements.
Okay.
But instead,
Remember
they found evidence that the uranium atom was splitting a process that released an extraordinary amount of energy.
Okay.
This was completely unexpected
Right.
and initially contradicted existing theories.
So what do they make of this strange result?
Well, it was Lise Meitner,
Okay.
a physicist who had been forced to flee Nazi Germany and was working in Sweden at the time, who played a key role in understanding the significance of Hahn and Strassmann's discovery.
So they're poring over this data, trying to make sense of it all. And
They had this incredible aha moment while walking in the snow, discussing Hahn's results. It suddenly dawned on them.
yeah.
The uranium atom was splitting,
Wow.
releasing energy according to Einstein's famous equation in Inertia.
Wow, what a moment. I can only imagine the feeling of realizing you've stumbled onto something so profound,
Yeah.
so world-altering.
Uh-huh.
And the implications of this discovery must have been immediately apparent, right?
Oh, yeah.
This wasn't just some esoteric scientific finding. It was the key to unlocking a whole new level of energy.
Exactly. The news of fission reached Niels Bohr in the United States, who immediately grasped its potential.
Okay.
He raced to tell Enrico Fermi and others, and the race to understand and control this new form of energy was on.
And that's really where things start to heat up, both scientifically and politically. We'll delve into that in our next part.
Absolutely. So as scientists are racing to understand this newfound power of nuclear fission, one figure really stands out with his early warnings about the potential consequences.
Yeah.
Leo Szilard.
Szilard was an interesting character, wasn't he?
Yeah, very much so.
He seemed to be constantly thinking several steps ahead, even back in the 1930s.
Yeah.
It's like he had this almost prophetic vision of a world with atomic bombs,
Yeah.
long before anyone else was even considering it.
It's almost like he had a Cassandra moment, where he knew something terrible was coming but couldn't get anyone to take him seriously. He understood the implications of a nuclear chain reaction,
Right.
where splitting one atom could trigger a cascade, releasing an unimaginable amount of energy.
So he was worried that this discovery meant for scientific advancement could be twisted into a weapon of unimaginable destructive power.
Absolutely. Szilard became deeply concerned about the potential for weaponization. He even tried to keep the discovery of fission under wraps, hoping to prevent it from falling into the wrong hands.
But trying to suppress scientific knowledge is like trying to hold back the tide,
Yeah.
especially with a discovery as significant as this.
Yeah.
It was only a matter of time before the implications became clear to others as well.
You're right. The cat was already out of the bag.
Right.
With the war in Europe escalating,
Yeah.
the race to understand and control this new force just intensified.
Mm-hmm.
It wasn't just about scientific curiosity anymore.
Right.
It was about national security survival, even.
I imagine the atmosphere in the scientific community must have been electric.
Oh, yeah.
With anticipation and a sense of urgency, did scientists in different countries collaborate?
Yeah.
Or was there a sense of secrecy and competition?
It was a complex mix of both.
Yeah.
While there had always been a spirit of international collaboration in science,
Right.
the looming war cast a long shadow.
For sure.
Scientists in the United States, the UK, Germany, and elsewhere knew that the first to harness the power of fission could hold a decisive advantage. So while there were still some attempts at sharing information, there was also a growing wall of secrecy.
So it became a race against time, a high-stakes game, with the future of the world hanging in the balance.
Yeah.
In the midst of all this, a team led by Enrico Fermi at the University of Chicago achieved a major breakthrough.
Yes, they did.
What was their contribution to this story?
Fermi's team created the first self-sustaining nuclear chain reaction in 1942.
Okay.
They proved that it was indeed possible to harness the energy of the atom on a controlled scale.
So they moved from theory to reality, from equations on a blackboard to a tangible demonstration of this immense power.
Right.
That must have been a pivotal moment, both scientifically and historically.
Absolutely. Their experiment, conducted in a squash court beneath Stagg Field at the University of Chicago, marked a turning point.
Wow.
It ushered in the atomic age and set the stage for the Manhattan Project.
The Manhattan Project, that code name has become synonymous with the race to build the atomic bomb. What can you tell us about this massive undertaking?
It was a top-secret project launched by the United States government with the goal of developing an atomic bomb before Nazi Germany could end. It involved thousands of scientists, engineers, and technicians working in secrecy at locations across the country.
It was a monumental effort driven by a combination of scientific ambition and the fear of what might happen if this technology fell into the wrong hands.
Yeah.
And what were some of the key scientific challenges they faced?
One of the biggest hurdles was the need to separate the rare uranium isotope U-235 from the more common U-238.
Okay.
U-235 was the key ingredient for a fission bomb.
Right.
And separating it proved to be an immensely complex and resource-intensive task.
It wasn't just a matter of mixing ingredients in a lab.
Yeah.
It involved creating entirely new technologies and industrial processes on a massive scale.
Precisely. It involved building enormous facilities like Oak Ridge in Tennessee, dedicated to isotope separation. They explored various methods from gaseous diffusion to electromagnetic separation, each with its own challenges and complexities.
So they were pushing the boundaries of science and engineering simultaneously.
Yeah.
All while working under intense pressure and secrecy, and all of this had profound moral and ethical implications, didn't it?
It did. The scientists involved in the Manhattan Project were acutely aware of the destructive potential of the weapon they were creating.
Right.
They understood that they were unlocking a force that could change the course of history, and not necessarily for the better.
It must have been a constant struggle for them, reconciling their scientific curiosity and dedication to their country with the knowledge that their work could lead to unprecedented devastation.
Many of them, including Szilard and Bohr, wrestled with these moral dilemmas.
Right.
Even as they worked tirelessly to develop the bomb, they also sought ways to control its use and prevent a nuclear arms race. It was a time of immense scientific achievement, but also deep moral introspection.
Their story reminds us that scientific progress is not just about equations and experiments. It's also about the choices we make, the consequences we consider, and the responsibilities we bear. The Manhattan Project was a testament to human ingenuity, but it also served as a stark warning about the duality of scientific knowledge, its potential for both good and evil. You know, it's incredible how this story, intertwines these grand scientific concepts with the very human element of personality.
Oh, absolutely.
Richard Rhodes does a great job of bringing that out.
Yeah, he really does.
In the making of the atomic bomb.
Yeah.
Like the anecdote about Rutherford being so skeptical of theoretical physicists until he met Bohr, who he described as a football player.
Yeah. It's a perfect example of how, preconceived notions can be challenged by simply getting to know someone.
Yeah.
And in this case, it led to a really fruitful collaboration that advanced our understanding of the atom.
And speaking of personalities, the book also delves into the fascinating dynamic between Heisenberg and Bohr. regarding the interpretation of the uncertainty principle.
Yeah.
They both played key roles
Right.
in developing quantum mechanics.
You did.
But they had very different ways of approaching it.
Yeah.
What was the core of their disagreement?
Well, Bohr, with his philosophical leanings, really embraced the idea of inherent ambiguity in nature. He accepted that there are limits to what we can know.
Okay.
And that some things might always remain uncertain.
Yeah.
Heisenberg, however, focused more on the mathematical formalism.
Right.
He seemed to really struggle with the idea that we might never have a complete picture of reality.
It's almost like their debate reflects the very principle they were grappling with.
Yeah, it really is.
But amidst these theoretical discussions, there was this pressing real-world concern about the potential for a nuclear chain reaction.
Right.
Szilard, as we discussed, was already sounding the alarm about this back in 1939.
He really was, and that's where Szilard's personality really shines through.
Right?
He wasn't just a brilliant theorist.
Yeah.
He was also deeply pragmatic and a man of action. He understood the magnitude of what they had discovered and really felt a moral imperative to warn the world about the potential consequences.
Yet his warnings were initially met with skepticism and even resistance.
Yeah.
Why do you think that was?
Whoa.
Was it simply the difficulty of comprehending such a world-altering possibility?
I think so.
Or were there other factors at play?
I think it was likely a combination of factors. The concept of a weapon with such destructive power was hard to grasp for many people at the time.
It was unimaginable.
It really was.
At the time.
And there was also the political context. The world was on the brink of war, and there was this reluctance to believe that something so terrible could be unleashed.
Yeah, it's a classic case of denial, perhaps.
Right.
When faced with a terrifying possibility. Sometimes the easiest response is to simply dismiss it.
It is.
But Szilard was persistent.
He was very persistent.
He understood the urgency of the situation.
He even enlisted Einstein to write a letter to President Roosevelt outlining the potential danger and urging the U.S. government to take action. But even that didn't immediately lead to a full-scale effort to develop an atomic bomb.
It seems like bureaucracy often moves at a glacial pace, even when faced with existential threats.
Yeah, you could say that.
What was the turning point that finally led to the Manhattan Project?
I think it was the attack on Pearl Harbor in 1941.
Okay.
It was a wake-up call for the United States.
Right.
And it shifted the public perception.
Yeah.
And really made the threat of a potential enemy developing an atomic bomb much more real and urgent.
So the context of war, sadly, often becomes the catalyst for rapid technological development.
Seems that way.
And then the Manhattan Project really was this unprecedented mobilization of scientific and industrial resources.
Right. It was, imagine entire towns springing up overnight.
Wow.
Shrouded in secrecy, all dedicated to unlocking the secrets of the atom.
It must have felt like stepping into a science fiction novel.
It must have.
But with very real and very high stakes.
Oh, absolutely.
And through it, all these scientists, engineers, and technicians were carrying the weight of knowing that they were creating something that could potentially end civilization as we know it.
They were.
That's a heavy burden to bear.
It is a heavy burden to bear, and the book really captures the moral dilemmas they faced.
Yeah.
On the one hand, they were driven by scientific curiosity, patriotism, and perhaps even a sense of destiny to harness this incredible power.
Right.
On the other hand, they were grappling with the potential consequences of their work.
It's a stark reminder that scientific progress isn't a purely objective endeavor.
No, it's not.
It's always intertwined with human values, ethical considerations.
Right.
And the choices we make about how to use our knowledge. The Making of the Atomic Bomb isn't just a science book. It's a story about humanity at a crossroads.
It is. It's a story about the immense power of human ingenuity, but also a cautionary tale about the responsibility that comes with that power.
Right.
As we've explored in this deep dive, the atomic age was born from a convergence of brilliant minds, groundbreaking discoveries, and complex historical circumstances.
Yeah.
And the legacy of that age is still with us today, shaping the geopolitical landscape and forcing us to confront the ethical implications of powerful technologies.
So what's the takeaway for us, the inheritors of this legacy? What can we learn from this journey into the heart of the atom?
Yeah.
Perhaps it's that knowledge is power.
Yeah.
But power without wisdom is a dangerous thing.
I think that's a profound insight.
Yeah.
The making of the atomic bomb really compels us to ask those difficult questions about the limits of scientific inquiry, the responsibility of those who wield powerful knowledge,
Right.
and ultimately how we can ensure that our technological advancements serve humanity's best interests.
It's a conversation that needs to continue
It does.
long after this deep dive is over.
Absolutely.